My name is Alex McLennan, and this is my project on waveguides. Waveguides are kind of like transmission lines. Transmission lines are used to carry a signal from one point to another. At lower frequencies, these are usually pretty good because they're basically lossless. However, at higher frequencies, transmission lines can be quite lossy. Waveguides are very low-loss devices at higher frequencies. So for applications such as satellite communications, waveguides become very important to sustain reliable communication. To understand how waveguides work, we need to use Maxwell's equations to get a system of differential equations so we can see how the electric and magnetic fields behave. Here are the two equations that I use to generate a system of equations. To use these equations, I evaluate the curl operators and then broke the E and H fields into X, Y, and Z components to give a system of first-order differential equations. Here's the entire system of first-order differential equations from the curl operators of the previous equations I showed, broken down into the X, Y, and Z components for the H field and the E field. To solve this system, I take advantage of the fact that the electromagnetic waves can be expressed as transverse magnetic and transverse electric waves. Transverse magnetic means that the magnetic field components are parallel to the plane of propagation, and transverse electric is the same with the electric field. For transverse magnetic waves, or TM waves, the electric components in the X and Y are always equal to 0, and the HZ component is always equal to 0. So because the magnetic field is always existing parallel to the plane of propagation, and if the wave is propagating in the XY plane, the H field will always be in the HX and the HY components. This means the electric field only has a Z component. So then all of the equations simplify to the one shown. In my simulation for this project, I focused on TM waves. So using the central difference and Yi's grading strategy, I came up with the following finite difference equations. You can also see that the H field is defined on the half time steps, while the E field is defined on whole time steps. Also, the E field is defined on whole spatial steps, while H field is defined on the half spatial steps. We'll come back to these difference equations in a little while. But first, let's take a look at the Yi's grading strategy to give us more insight into how the spatial grid is divided up. Okay, so here's what a normal grid might look like for a specific problem. Around the edges, I've just made it a perfect electric conductor just to give some boundary condition to the space. All of the Okay, so if we focus down here to see that the origin starts there at I1, J1, and all of the dots on the solid line represents the whole grid, and all of the dotted lines represent the half grid. So I've drawn out here that the E sub Z component is on the whole grid for both the X and the Y, so it's always going to be on the dots that go throughout the entire space. The H sub X field, however, is on the whole X but the half Y grid. So that's where you see the stars that I've drawn in between on the whole X grid but the half Y. And the same thing for the H sub Y, except for it's on the whole Y but the half X. So to give you a better idea, I drew this grid so you can see that it's drawn out. The solid lines represent the whole and the dotted lines represent the half, and I've drawn out the variables with their components in their respective places as it'd be laid out in the grid. The thing that I don't show here is that the E fields are all on the whole time steps while the H fields are on the half time steps. So you can imagine the staggering in time as well as the staggering in space.